Okay, good. Welcome back, everyone. Small class, huh? 4 people in classroom.
I'm missing like 2 people.
Thank you.
He didn't even move anymore.
All right.
It's recorded.
All right, so hopefully you submitted your project phase 2. Okay. We are going to move on to the phase 3. So let's just take a quick look at what's expected. Not there. What's expected for phase 3. Just a quick preview of what's expected for phase 3. So right now, okay, we are in unit C4, which is Venn diagram. We're going to start Venn diagram today. And after that, unit C5 is just an example. I'm probably not going to spend much on C5. C5 is entirely like the example of performance computation. So right after C5, you're going to do project phase 3. This is performance computation. This is actually almost nothing to do with X-Prior5 by itself, but you're going to use X-Prior5 to provide important information to compute performance. In other words, there are sets of data you need. You're going to select your power plant associated with possibly propeller, comes with catalog spec of brake specific fuel consumption BSFC, and also propeller efficiency. Those are catalog specs. You're going to choose your own power plant and try to integrate into X-Prior5. In other words, if you install your power plant, it is going to affect on your location of weight distribution, and the center of gravity is going to be determined. So once you determine center of gravity, that information is quite important for phase 4, which is the stability analysis. Stability analysis requires identification of center of gravity and also neutral point. Okay. So X-Prior5 is being used, but it's not the main thing. In other words, X-Prior5 is going to provide you 2 information. One is aerodynamic design results and also integration of propulsion, overall weight distribution of your airplane. So those are the information required for the beginning of phase 3. Phase 3 is going to require, okay, of course, your airplane is configured, and then you're going to choose the best configuration of the team. You're going to start from there. Then, of course, the choice of propulsion system is going to determine TSFC, BSFC, propeller efficiency. So in other words, thrust or power available is going to come into play once you choose your propulsion system. And also, thrust/power required is essentially how good your airplane is. If your airplane is pretty bad, this is pretty high value. Okay? And you're going to begin integrating structural materials that actually determines the weight of your airplane. And some other constraints such as special thing, cowling, landing gear. If it's manned airplane, you're going to integrate your cockpit block. Heavy lift airplane such as SAE, you're going to specify, okay, this is required payload. You have to integrate those things. Okay? That is going to affect on center of gravity location and also neutral point of the entire airplane. And then if the neutral point is forward of center of gravity, that's a big issue. Your airplane is unstable. So you have to do something. You have to shift your neutral point by increasing the volume of tail or some other things. Okay, configuration change might be required for the phase 4. Now, at this moment, don't worry too much about that. Stability is not going to be discussed in phase 3. Okay, so phase 4, because of the needs of making your airplane stable, you may change some configuration, but it's probably not going to happen in phase 3. Okay, so phase 3, big thing is you're going to, of course, plot power or thrust available versus power or thrust required plot. Okay, thrust plot and power plot. Of course, that is going to determine so many performance characteristics. Okay, it is going to determine endurance, range, climb rate, max climb angle, power of glide ratio, minimum sink rate, takeoff and landing constraints, turning, and also other things. Okay. So you're going to compute those and then list it as a tabulated form and then provide the result of your airplane. And then some of the designs you actually come up with the conclusion that our design actually meet the initial goal we set. Okay. And then if your team realizes that, hey, this airplane doesn't satisfy anything, that means, well, we designed a very crappy airplane. We have to do something. So that could possibly happen at the final stage, phase 4. Okay. So phase 3, don't worry about it. Phase 3, you are going to basically go through the first round of your design process and come up with actual performance. Then at that point, you realize that, hey, our team did a great job. This is a piece of crap, but this is not airplane we want. You're going to come up with that kind of result. Okay. Then toward the end of phase 4, you're going to at the same time stability analysis and optimizing your design. Okay. So that's sort of like my plan. I hope it works well. If every team outperforms my expectation, great. I will be happy. It may or may not affect on your final course grade. Final course grade is sort of independent. If everybody did terribly poor job, it's okay. I mean, I'm okay with it. This is entirely virtual reality. It's not real. No one dies.
Yeah.
Okay. No problem. So just to do your best and find out as much as you can using the software-based design process. This is fairly new, but this is a main trend of today's airplane industry, of course. The traditional style of, let's build it, test it, break it, or run something, let's build it again, test it, and then test pilot dies, well, let's build another airplane. That's traditional style. Nowadays people just don't do that. Okay, so I hope this is your very good experience. Software simulation-based optimization process. Before you even build an airplane, you can sort of predict your performance. I want to see that. Okay, so just take it easy, just do your best. But suppose if your team did the horrendously bad, poor job, I really wish everybody else does kind of sort of like poor job. In other words, do not make your team stand out. Hey, this team is so bad that actually making the professor think twice. Wait a minute, should I pass those guys or what? So let's just avoid that. Okay. In other words, a tremendously poor job is let's get started. Like, we have I don't know 4 hours more. Let's just do something before due date and time. That's a bad decision. Some of the aero students choose to do that. None of them will pass. I hope it doesn't happen in this class. I'm not going to name who, but some group of people in aero constantly do that. Okay, never meet my expectation. Period. Okay. Anyways, I hope it doesn't happen here. This is not aero. This is flight mechanics performance. You passed aero. Any question about the phase 3 project? So you're doing okay, right? So far, phase 2, up to phase 2, you are sort of enjoying and kind of get used to the software. Software is cranky, but you kind of know how to do it. And then you come up with some kind of airplane design in your hand, but I'm not sure if I really build it or not. Okay. All right. So today, let's get started on BN diagram, unit C4. Okay. All right. So BN diagram. So now we are going to start talking about airplane maneuver. We want to have a very maneuverable airplane, but at the same time, that's a trade-off. Lots of trade-off. You want to have a very strong engine, which comes with lots of excess power available. That's very good thing to begin with. However, it is going to make your airplanes very bulky, heavy, and also performance and maneuver requires very strong structures. If you are designing and building everything out of balsa wood, you cannot really maneuver well. Okay, that means BM diagram wise, your flight envelope is kind of limited. And then especially low speed, if you're trying to do a high G maneuver, it is also very difficult because before you do a high G maneuver, your airplane may stall. So the stall characteristics is going to be a constraint factor for BM diagram for low speed and high speed. It is essentially how strong your structures are. Okay, so let's just take a look at BM diagram. This is commonly called flight envelope, right? Of course, when you design your airplane, you have to take a look at BM diagram. So the subject here, I'm going to cover BM diagram, energy, height, and specific excess power. Those are the required engine excess amount of power for your maneuvering and also climbing. Climbing, maneuver, acceleration, all of those things requires excess power. If you don't have any excess power, only thing you can do is just a sustained level flight. That is going to limit how high you can climb up. Okay, that's called energy height. And then, so we're going to take a look at the PS diagram. PS is the specific excess power. That's called PS. PS diagram is quite important. It shows up all the time. And also maneuverability diagram, it also shows up all the time. Okay. And then the second half of this unit C4, I'm going to introduce constraint analysis. In other words, this is the constraint of the design. I want to have my airplane with these constraints to begin with. Where is the design space? So we are going to find out the design space out of those constraints. Suppose if we want to have an airplane which flies supersonic and maneuver just about outmaneuver any airplane imaginable, and then take off and land in very short distance. If that's the constraint, you have to somehow find out what is the airplane that actually satisfies all of those constraints. It's not easy. So you're going to draw a constraint diagram and find out design space. Okay, that is going to be your final quiz. Quiz 5 is going to show up. It's going to be constraint analysis, quiz 5. Okay, so be expected. You're going to have a final quiz, quiz 5. Since this is final quiz, I don't know, it's probably more than out of 10 points. It's like a boost up bonus toward the end. Constraint analysis, quiz 5 is going to show up. Okay, so having said that, let's just take a look at the real thing. Okay, if you go to handout C1A T38 data, let's just take a look at this one. So this is the real data, T38 performance data. Okay, if you go scroll down quite a bit, of course it is going to give you CO alpha curve with lots of configuration flaps. This is the CDO, parasite drag coefficient over the transonic supersonic. This is wave drag. This is drag due to rift factor. So this is induced drag change over the transonic supersonic range. Yeah, this is the thrust diagram for sea level, higher altitude, higher altitude, higher altitude, and higher altitude. This is a power diagram. And this is power for higher altitude. So this is a BN diagram, right? So this is BN diagram for a different gross weight. This is 9,600, yeah, 9,600 pounds gross weight BN diagram. Okay. So this is product sea level 15,000, 25,000. So this is BN diagram for T38. This is another BN diagram for 12,000 pounds gross weight. Okay. And then what is the altitude? The altitude is variable. Okay. Okay, good. So next one, this is a maneuver diagram. You know, we're going to cover that also. This is actually composite plot. You can read off lots of information from here. So suppose for the next exam, I can give you, hey, this is the information. You can read off lots of things, such as what is the minimum turn rate. Well, actually, maximum turn rate, so not minimum. Minimum turn radius, maximum turn rate, what is it? And then what is the corner velocity? What is the Q limit? Other things. You can read off lots of things out of this. This is a maneuver diagram. For this is a configuration of 15,000 feet altitude, 1,400 pounds fuel load. This is the same thing 2,000-pound fuel road, 15,000 feet altitude. MSL means mean sea level. Okay. So this is a real thing. So we're going to cover this. Those are maneuver diagram. So this is a TS diagram. Okay. So let's get started. So let's look at the first page, BM diagram. So this is the schematic of BM diagram. Of course, you probably know already. BM diagram. Oops, I don't have a pen. I keep forgetting the connection. Okay. So there are a few important things I'm going to kind of point out one at a time. Okay, so BM diagram, this is going to indicate, this is the limitation for the aircraft, which is the ability to generate the lift or sustain the structural loading needed to perform a specific turn. Okay, so first thing is, of course, this is a positive structural limit in high speed. In other words, this airplane can only take up to about 7G positive, okay? And the negative G wise looks like negative 3G. So this is the positive and negative structural limit. If you go for higher G, you have a risk of breaking airplane, okay? Q limit here. This is the maximum dynamic pressure you can have. In other words, if you go beyond that, you're going to damage your structures. This is going to actually constrain your maximum speed. In this airplane, this is 300 knots, right? Calibrated airspeed, 300 kcs. That's what you have. Now, for lower speed, this is the positive side, positive maneuver, lower speed, and the limitation is based on the stall, okay? In other words, if you try to pull like a high G maneuver, before you reach that load factor, your airplane actually will stall. So the limit is a stall. Okay, so this is called positive stall limit. This is negative stall limit, especially road speed end. Okay. Now you have multiple equations. Actually, it shows here. This is, by the way, stall boundary. Like I said. So this is the positive stall boundary, this is negative stall boundary. So the stall characteristics is going to be the factor to determine your flight envelope for low speed. Now high speed is going to be like limited for the maximum G your structures can take. Okay. And then this is the equation for the maximum load factor. It really depends on how much maximum lift coefficient you can produce and also how heavy your airplane is, mainly, okay? And then this is much more generalized stall speed. Now, stall speed now includes the load factor here, okay? So this is stall speed is going to be a stall boundary right here for the lower side of the airspeed, okay? Now, vertical line labeled Q limit, this indicates the maximum structural airspeed of the aircraft, usually the critical Mach number for high-speed airplane. Some of the teams designing transonic transport, which is, I believe, Connor and Matthew, is that correct? Let's just double check if they are online. I have, wait a minute. Oh, hey, Connor. And Matthew, are they listening? Can you hear me?
Yes, we can hear you.
Okay. So your design is like a transonic transport, isn't that right?
Yeah.
Okay.
Yeah.
Got it. Just checking. So I think one of the important design parameter is you guys need to come up with critical Mach number. This is required because you're talking about transonic airspeed. So this is going to be probably corresponding to a Q limit, okay? All right. And then pretty much everybody else is low speed. So critical Mach number probably is not that important, okay? All right. And then one important thing is something called corner velocity. Okay, this is just a spillover. This is not part of this example. Sorry about that. Corner velocity, something called B star. Okay, so this is the velocity at which the stall limit and the structural limit makes a corner of the graph. That is essentially the quickest, tightest turn which your airplane can have. This is a condition. So corner velocity is, if you go back right here, this is a corner velocity. Okay. Okay, right here. So in this case, I don't know, it's 220-ish kcas is a corner velocity for this airplane. Okay. All right, so let's just take a look at example C for one very easy plug and check example. Let's just do it. Okay. All right, example C for one. An aircraft with a wing loading. Wing loading can be defined by weight of the airplane divided by wing area, which you know that. High wing loading airplane is, of course, it's not desirable because it is going to be very difficult to slow down. Stall speed tends to be higher. Okay, what is the typical look of a high wing loading airplane? The airplane sitting right next to the bookstore. Okay, the airplane with this kind of wing. High wing loading, yeah, that's right. Do you want to ride on that? No, no one wants to. It's a terribly bad low speed. Well, low speed characteristics is so bad. Anyways, okay. So, an aircraft with a wing loading 70 pounds per square foot, and then CL max is 1.5. Okay, has a maximum structural load limit of 9. Whoa, 9 is pretty high, but anyways, what is the corner velocity at sea level? We are going to just basically plug into this equation. Okay, it's a very simple exercise. So corner velocity B star is equal to square root. Okay, 2 times n max is 9. Weight of the airplane is where? The weight is not given. Weight over the area is given. So let's just modify the equation a little bit. Sorry about that. Let me just modify the equation because it's much easier. So this is going to be, you're going to change the form a little bit. So you're going to specify 2 times n max over rho CL max. And this is W over S. This is the wing loading. Okay, so we're going to just plug in the value here. 2 times n max is 9. This is 9g. Density, let's plug in sea level 0.002377 slugs cubic foot. Okay. CO max given 1.5. W over S is 70 pounds per feet square. If you compute corner velocity, you get 594.5 feet per second. Yeah, it's very simple exercise here. So this is the corner velocity for this airplane. Pretty high speed. Okay. So next page, let's just take a look at very, very important subject. This is going to be probably showing up on exam 2. So you really need to master how to read off this chart. This is called PS diagram. And also following pages, you can see actually maneuver diagram, which is this thing, okay? So this is called maneuverability diagram. The other one is PS diagram. Let's just take a look at PS diagram to begin with, okay? So this is energy height and specific excess power. So first of all, this is Table 1.2, typical minimum design requirements, constraints for a multi-role jet fighter. Again, constraint analysis is usually the very first step when you do a design process. In other words, this is a requirement. Requirements are constraints. List of constraints shows up first, and then those kind of things need to be plotted to find out your design space. Design space is, okay, how big your airplane range should be, kind of thing, okay? If you want to satisfy this much constraints. So this is the constraints. Combat mission radius 400 miles, weapons payload, takeoff and landing distance, Mach number, instantaneous turn rate, specific access power. This is one of those constraints right here, as you can see. So even before you start beginning your design process, in this case, specific access power is required. So this is a 4G at the Mach number 1.2, 20,000 feet mean sea level at the WMAN. What's WMAN? WMAN is the aircraft weight with 50% internal fuel, 2 times AIM-120 AMRAAM, advanced medium range air-to-air missiles, and the full cannon ammunition, but no air-to-ground weapons. So this is maneuver weight of airplane, okay? So for a maneuver weight of an airplane at 20,000 feet mean sea level, you need to have Mach number equal to 1.2, 20,000 feet, 4G, specific access power. Okay, so this is actually going to determine how strong your power plant should be in order to have this much maneuverability provided, okay? This is a sustained load factor, 9G, blah, blah, blah. Okay, so this is quite important information. Specific excess power. Let's just start our discussion with specific energy. This is oftentimes called energy height. This is actually much easier to understand. This is energy height. That means if you combine potential energy and kinetic energy, it is going to be converted to the unit of height. That's called energy height. So when you fly your airplane, obviously it's a trade-off between kinetic energy and potential energy, how high you can climb up and then sustain your level flight. When you sustain your level flight, you're flying with certain airspeed, which includes kinetic energy, and also potential energy is your altitude. Now suppose if you give up all the kinetic energy, you can climb up more, but you cannot sustain your level flight. In other words, you climb up and velocity is 0. That's absolute maximum height you can climb up. That's called energy height. Okay? So let's just think that way. So this is energy height comes up with the unit of height. Okay? Now, let's talk about, okay, specific excess power. Specific excess power is, this is the excess power. This is power available minus power required, okay? Now, this is the aircraft's power that can be used to increase its potential and or kinetic energy. It's called specific excess power. That's called PS, okay? PS is essentially PA minus PR, available power minus required power divided by weight of the airplane. So this is normalized by airplane weight. That's why it's called specific excess power. This is quite important, PS. So oftentimes we call PS diagram. Next page, we are going to look at the PS diagram. So this is going to tell you how much specific excess power you have. PS diagrams, okay? So I'm going to kind of open up another file. Okay. So this is PS diagram, page 4. Let's take a look at page 4. Now, interesting plot here. So you have a 1 and 2 plots, figure 542. This is a PS diagram for a multi-role fighter aircraft at the load factor equal to 1. Load factor 1 typically means just a straight level flight, okay? So when you do maneuver such as this is a load factor n equal to 5, so this is positive 5G, maybe turn or something, okay? So this is like a 5G turn. And then those are the contour lines. interesting. Contour line is, this is a line of constant value of PS. So this is the line of a PS, specific excess power, 800 feet per second available around this line. This is a line of 600, 400, 200. You have to take a close look at this one, which is PS equal to 0. That means, what do you mean? So this is, you can only do level flight. You cannot accelerate. You cannot climb anymore. In other words, that's it. This is the flight envelope. Okay?
That's your ceiling.
You can determine seating, yes. Okay, because you cannot climb up and sustain anymore. So this actually determines lots of things. This is going to determine your maximum level flight airspeed. This is going to determine, okay, so what is the seating? This is going to determine, okay, how much minimum speed you can sustain without stall. Lots of things you can determine, okay? So flight regime within this envelope is called flight envelope. Good. Okay, so let's just go back here. So this is a PS diagram for a multi-role fighter aircraft. PS values are indicated by contour lines, yes, okay? So this is a three-dimensional with altitude as the third dimension. This is the power available, power required curve. PS equal to 0 is the aircraft's operating envelope. Okay. Okay. So if the PS is more than 0, that means aircraft can still climb or accelerate. You still have excess power. But PS equal to 0 means your airplane is flying just all thing you can do is just a level flight. Okay. No acceleration, no climb anymore. Okay. And you can determine absolute seating, which is the aircraft's absolute seating would be the highest point on the PS equal to 0 contour. Where is it? Let's just take a look. Where is it? Right here. Let me change the color here. So this is airplane's absolute seating. What's the value here? Anybody? Something like, yeah, something like that. We're going to find out. It's going to be example. So this is going to be absolute seating, right? Okay. And likewise, you can actually determine service seating. In other words, service seating can be defined by the highest point on its PS equal to 100 feet per minute. What is feet per second corresponding to? Feet per second. Basically multiplied by 60. 60, right? So no, divide by 60. Divide by 60. So 0 point? 1.67 feet per minute?
Yeah.
Okay.
Or feet per second.
Feet per second, okay. So if you take a look at this plot, man, it's hard to. So suppose if you have another contour, PS equal to what, 1.67 feet per second contour. Suppose if such a contour is available, such as this, you know, I can only imagine, but suppose if this is, let's say, PS is equal to 1.67 feet per second contour. Right here is your service seating, right? This is your service seating because you can still have this much PS. In other words, still have your capability to climb up. That's service seating. This is like absolute seating. You cannot climb up anymore, okay? And combat seating is like what, 500. So again, it's a little bit lower, okay?
Are we assuming that's for maximum power?
I guess so. Yeah. In other words, yeah, let's take a look at configuration. 50% internal fuel, 2 AIM-9. Maximum thrust, that's right. You're right. Maximum thrust, maximum installed thrust.
Yeah.
That's
what
right.
I'm asking.
That's right. And the weight is 21,737. This is weight of maneuver, which is based on this configuration. This is load factor 1, so the double flight. This is maneuvering, load factor 5. So it's probably like a sustainable turn, horizontal. Okay. Anyways, the aircraft's absolute maximum speed in level flight occurs at the altitude and Mach number where PS equal to 0 contour reaches farther to the right. What? That is, where is it? Right here. So this is going to be airplane's maximum level flight. Okay. Altitude is not the sea level, something like this. So this is the altitude of your airplane's maximum level flight airspeed. This is true airspeed. So 1200 ktas at altitude, I don't know, 45,000 feet, I would say. So you can read off lots of things, right? Absolute seating, service seating, maximum level flight airspeed, and even more. Okay. Now let's talk about zoom climb. This is quite important. In other words, sustainable absolute seating is basically you can sustain your level flight at the same time. This is maximum you can climb up. Now suppose if you give up all of those kinetic energy, you can climb up more. That's called zoom climb. In other words, starting from here, you're going to actually accelerate. No, you cannot accelerate, but you're going to climb up by giving up your velocity. So you can still climb up, but as you climb up, you're going to lose your velocity, and then reaches to 0 velocity. That's zoom climb. So zoom climb is basically you're going to reach out to the energy height. Okay. Energy height is kinetic energy and potential energy all combined, how much climb you can have. In other words, you're going to give up entirely. Kinetic energy is going to be converted to the potential energy. That's called energy height. So let's just take a look at it. If the aircraft whose PS diagram is here, absolute seating point, which is 57,630 knots away, its absolute seating point is right here. Okay, so the question is, can you still climb up beyond that point? Yes, you can. How much? In other words, you're going to start doing zoom climb. You're going to give up your kinetic energy and then gain more altitude, but as you reach out to that maximum altitude, you have 0 velocity. How do you read out? You're going to follow along this line. This is a zoom climb. As you reach to the 0 velocity, you can reach to this point, which is 75,000 feet altitude. This is energy height. So this is a line of 70,000 feet energy height line. This is 80,000 feet, and this is 60,000. So those are the lines of energy height, constant energy height. So you can actually still climb up to 75,000 feet, but the velocity becomes 0. This is corresponding to the energy height. Okay? So realistically speaking, if you start climbing from here, as you reach to the velocity 0, you can gain up to 75,000 feet altitude. But velocity is 0. Okay? It's not level flight. If you want to still have level flight, you are 57,000 feet. This is absolute seating.
So are you bleeding energy after that point then?
That's right. That's what I'm talking about, yeah. You basically trade off your kinetic energy to potential energy. Okay? Yeah. All right, so this is called zoom climb. So zoom climb actually gain energy height. energy height. Okay. And also another thing, you can get the information such as minimum time to climb. Okay. Also the maximum rate of climb. This is just the information, sort of kind of information you can get from PS diagram, but you can read off those information. The maximum rate of climb at any given altitude is at the speed where PS is maximum. This is quite important. So if you climb at the location where PS is maximum, it is maximum rate of climb. Okay. Now, minimum time to climb is slightly different. Minimum time to climb is achieved by changing energy height as fast as possible, and the aircraft increases energy height the fastest when it moves perpendicular to HE equal to constant lines. This is quite important. And also, if you are designing supersonic capable airplane, obviously when you climb up with maximum rate of climb does not necessarily mean the same as if you are doing minimum time to climb, because minimum time to climb requires you to go through the transonic region. Okay, first of all, you climb up with maximum thrust going over the peak point of PS, but at the same time as the transition comes in from transonic to supersonic, you actually want to accelerate, not like climb, then hit the supersonic and begin climbing. Let's just take a look. So the peak point of each PS diagram here, here, and here. Those are the peak points, right? So let me just repeat what I just said. The maximum rate of climb at any given altitude is achieved at the speed where PS is maximum. Those are the points. Okay. So right here and right here and right here, you are going to maintain maximum rate of climb. So you need to go through the flight envelope through here, here, here. Now, minimum time to climb is if you fly completely perpendicular to the energy height. So in this case, yeah, you can sort of doing that, not quite. And then minimum time to climb pass, if you wanna plot, this is the minimum time to climb pass. Actually, right here, you're going to go this way. Why? You're going to go this way. What's going on here? So this is the transonic region. So you're going to accelerate to hit the supersonic first, and then begin climbing in the region of PS peak. So this is, okay, so this is kind of getting, graph is getting crowded, but so here is the supersonic climb. This is subsonic climb. This is the minimum time to climb to the altitude. Okay. This is the transition. Transition from subsonic to supersonic. So at the transition region, you actually concentrate to accelerate, not to gaining altitude. Okay. So that is going to minimize the time to climb. If you fly through this peak point, it is going to be always indicating this point, that point, this point. Those are the maximum rate of climb points, because that's the specific excess power peak point for each altitude. Okay. Anyways, so you can kind of read off lots of information out of this plot. Okay. All right. And then this plot is, of course, something called maneuvering plot. In other words, this is load factor n equal to 5. So this is probably sustainable level flight 5G. Now, obviously, the excess power, specific excess power is quite a bit different. So if you're doing a 5G maneuver, this is your flight envelope basically shrunk. Okay. This is going to change all of those parameters here. Okay. So let's just take a look at example problem here. Okay. Before doing that, let me just clean up this figure because I'm going to use this figure. So hopefully I can kind of clear out this figure. Not to work. I think it's easier to come up with a new figure. But anyways. Yeah. Especially those small dots I cannot erase. Hey. Okay, looking good. Looking good. Okay. All right, let's just take a look at the example problem here. Okay. So lots of questions here. I can show you one PS diagram asking like 20 questions. That's very easy exam for me to create, so be ready for it. So example C42. For the aircraft whose PS diagrams are depicted in figures 542, 43, determine the following. So 8 questions we're going to take a look at one at a time, okay? First question is, what is the aircraft's maximum 1G level flight speed and what altitude does it occur? Let's take a look at this figure. So the question is, okay, what is the aircraft's maximum 1G level flight speed and at what altitude does it occur? This figure. Okay. So obviously, okay, where is it? So first of all, 1G flight means this figure. This is a 1G flight, okay? Load factor 1, so you're not going to look at this one. And what is it? Maximum level flight speed, anybody? That's right. That's right. So right here, correct? Okay. So 1200 true airspeed, KTAS, corresponding altitude right here. It's like 45,000 feet. Okay. All right. So the solution here. Number 1, okay. Maximum speed is at the point where PS equal to 0 contour goes the furthest to the right. This is going to represent, once again, this point, so 1245,000. So airspeed, 1200 knots through airspeed. And altitude H, 45,000 feet. Okay. Question 2. is the aircraft's maximum zoom altitude? Oh, maximum zoom altitude. Let's be careful. Absolute maximum. So what is it? So in other words, where is the entry point for this maximum zoom altitude? Entry point. By the way, people online are awfully quiet, so I'm going to probably bug them a little bit. Any idea? Any idea? I guess some of you probably know about that. So when you enter zoom crime for this situation, where is the entry point? Anybody? Are you guys online, or are you guys actually logged in and sleeping or something? Anybody? Holy cow, it's so quiet. I don't know what's going on. They might be working on homework of other class or something. So,
is that maximum altitude where it starts the zoom climb, or where?
Well, zoom climb is okay.
Ends up being zero.
Let's say zoom climb is you are somewhere on this PS equal to 0 contour. Okay. Suppose if you start zoom climb from here, you are going to get this much altitude by giving up all the velocity. Okay. Is this absolute max? Not quite. So where's the good entry point of this absolute maximum zoom climb? Here, right? Okay, that's right. So you have a right idea here. So suppose if you enter zoom climb from here, so this is you're flying absolute maximum airspeed for n equal to 1 level flight. Then you decided to go for zoom climb. You're going to go up like this.
So this means we don't know.
Well, you can guess. So this is 80,000, 90,000, 70, 80.
100, maybe 90, 98,000.
Wait, I don't think so. I don't think so. Wait a minute.
Is it the highest point?
I think I'm
Yeah,
going
like 100
crossover.
100 something.
Yeah. So okay. Yeah, that's right. So this line is this.
So that's 100.
Yeah. Okay. So this line is right next to it. This one. So this is 80, 90, 100, 110. So this is 110,000 feet. If you enter zoom climb right here, you can get energy height 110,000 feet. So that's the absolute maximum altitude you can gain by giving up everything. Maximum thrust, the velocity is 0, you can climb up to 110,000 feet. Okay? So let me just summarize it, okay? Okay. So number 2. So this is the what is the aircraft's maximum zoom altitude? So this is absolute maximum. Enter zoom climb. From B equal to 1200 ketas. Then you can reach energy height which is equal to 110,000 feet at B equal to 0. So this is absolute maximum zoom climb altitude or energy height. Okay. Okay. Question 3. What is the aircraft's best rate of climb at sea level? And what velocity does it occur? How can you get such an information? Best rate of climb at sea level. Sea level, right here, sea level. Okay. So you can only guess, but suppose at the sea level, you have this kind of contour, right? right? And so you're going to go through that. Sea level is what? Yeah, maybe around here. 500 something knots. And then we can never get maximum rate of climb. However, it is at least more than 800 feet per second. Because this is 800 feet per second specific energy contour. Okay? So which is more than that? Well, we can only guess. There's no number associated. So let's just write it down here. So number 3. Okay, what is the aircraft's best rate of climb at sea level? Best rate of climb, at least 800 feet per second or more at sea level. And if you guess velocity corresponding to it is 530 knots, ktas. Okay, you can only guess, so it's like a kind of like value, but you can still get the value out. That's the beauty of this PS diagram. Question number 4, what is this aircraft's minimum level flight speed at sea level? What causes this limit? Stall. That's right, stall is correct. So basically, where do you look at? So this is the sea level. What is the minimum speed? Right here. There. So this is the minimum speed at sea level. What limits this? Well, of course, if you fly slower than this, you're going to stall. That's what it is. So your answer is, okay. So this is a minimum level flight. Let's say, what is the value? You read off, huh?
160.
Textbook says 120 K test. Do you agree?
I said 130.
130-ish, or 120, 116, something like that.
Higher than half, I'm sure. Whatever.
Okay, 120.
Sure. Why not?
And then this is limited by stall. In other words, if you fly slower than this, airplane stalls. Okay. Question number 5. What is this aircraft's maximum level flight speed at sea level? What is the limitation for that? That's right. So Q limit, correct. So this is the absolute maximum dynamic pressure of your flight that your structure of your airplane can take. Q limit. So if you take a look at the value, it's where? It's right here. Okay, right here. Sea level. It's a Q limit. That's right. So 800 knots. KTAS. Limited by Q limit. If you fly more than this, your airframe actually breaks down. Okay. Question number 6. What is the maximum altitude at which this aircraft can sustain a 5G turn? What is the maximum altitude at which this aircraft can sustain a 5G turn? And at what speed does it occur? So where do you look at now? You're looking at this plot. Okay, so because this is 5G turn plot. So question is, what is the maximum altitude that this airplane can sustain at 5G turn? Where is it? right here, okay? Right here. So corresponding, like a little bit more than 30,000 feet, 600 some kind of knots, right? Okay, so it's just, so the number 6, so this is the n equal to 5, and this is absolute seating, which is 32,000 feet, okay, and velocity v is 670 knots for true airspeed. Okay. Question number 7. What is the maximum speed at which this aircraft can sustain a 5G turn, and at what altitude does it occur? Let's just take a look. So this one, you basically take a look at the furthest point, I don't know, somewhere around here. So this is going to be your maximum level flight airspeed when you do a sustaining 5G turn. Altitude-wise, about less than 20,000 feet, something like a fairly close to 870 knots, something like that, at this point, okay? So that means question number 7, maximum airspeed. So n equal to 5, maximum airspeed is about 820 knots for true airspeed, okay? And what is the altitude? Corresponding altitude is about 17,000 foot, okay? Question number 8, last question, okay? Last question is, what is the minimum speed at which this aircraft can sustain a 5G turn? At which altitude and airspeed does it occur? Huh? And what causes this limit? What do you mean? Which altitude? Okay. Minimum speed. Where is it? Minimum speed. So this is sea level, yeah? So right here. So it must be sea level right here. It's about 300 little bit knots. It's a stall. Okay, good. So let's just conclude this. So suppose if you're flying with load factor 5, what is the minimum speed? Minimum speed is 330 knots through airspeed. Sea level, h equal to 0 sea level. And then limit is, of course, stall. If you fly slower than this, your airplane stalls out. Okay. I can actually come up with a lot more questions. So it is very easy to create an exam like this. I just give you just the data. Okay, answer those questions, a series of questions kind of thing. So you have to be ready for it, okay? Do you have any question here? So let's just stop here because motivation is very low today. Everybody's motivated because tomorrow is a day off kind of thing. So as you come back on Thursday, we are going to take a look at PS comparison and also maneuverability diagram, and then we're going to probably finish up C4, most likely. I don't know. So anyways, let's just start thinking about phase 3, okay, of your project. Any question? Let's stop here today. Have a great break, okay? Tomorrow is a day off. And we're going to see you back on Saturday. Any question, online people? Have a good day. See you back on Saturday.
What are we going to do this evening?
You're gonna go over sources. And then we finish up.
Jordan, do you have any question?
doing what?
I mean, they.
Okay.
She says she's done at 3:30 on
Yeah.
March,
So.
so.